Hello, everyone. This is Prithvi Manjunatha. I am PI for the project we are going to present today. The topic today is evaluation of operational effects of connected and autonomous vehicles through microsimulation. This STRIDE project builds on a previous STRIDE project, and I'm going to be talking about that. And then after recap of that, I'll introduce other topics. This webinar, in case you are new to the STRIDE series of webinars, is part of the STRIDE webinar series, and STRIDE is the US DOT UTC for congestion mitigation, which includes all the universities that you can see on your screen, and University of Florida is the lead institution for the consortium. For today's webinar, this is going to be the flow. As I mentioned, I am going to recap the previously developed simulation framework from the previous STRIDE project. And then the presentation is going to flow with different upgrades, so to speak, we made with this framework. First is going to be incorporation of signal and trajectory optimization that I'm going to talk about. And then Sharif from Tennessee Tech is going to talk about vehicle dynamics. And then Dr. Michael Hunter from Georgia Tech is going to talk about incorporation of human-driven behavior of the human-driven vehicle in the presence of CAVs or AVs. And then we will go into the educational component with the results from the survey of practitioners and development of educational materials with Dr. Hugo Zhao at Auburn. With that, so this is the UF team that worked on the project. Thanks to all the people who are part of this. There were 2 students who graduated and became doctors after this project. And with that, this project builds on an existing VisSim simulation framework that we developed a couple of years ago. So when we started that work, the idea was to evaluate VisSim capabilities and see how best we can model CAVs in a simulation framework using VisSim. What we found was, we can take advantage of 2 functionalities that VisSim offers. One is the COM application programming interface, and second is the external driver module. The COM API, it is helpful to access all the network elements during the simulation, whereas the external driver module, it's very good in accurately implementing specified acceleration or speeds for a given vehicle. So with using a combination of the COM API and the external driver model, we came up with this framework for simulation where we said we capture all the traffic data using COM API every simulation's second or interval. And then we feed it into whatever the AV or CV logic one would like to run. And then the acceleration for all the vehicles that are being controlled would be inputted to COM API and then written into a text file where the EDM picks up the text file and implements that for those vehicles every simulation time step. So this is like the basic framework. I forgot to mention, in case anyone has any questions during the presentation, please keep posting them on the Q&A tab that you can see. Since we are 4 speakers, we will try to dedicate 10 minutes for Q&A at the end of the presentation, and we'll try to answer them at the end. So we started with this simulation framework, and for this particular project that we're going to talk about today, we had 3 different types of upgrades to this simulation framework. When we completed this evaluation, at the time, we just used an AV model from the literature, and then a CV model based on what PTV had. And we ran this in conjunction with an emissions model that was developed based on the MOVES model by Georgia Tech. So that was the previous project. What we did in this project was we added the signal and trajectory optimization component, we added the vehicle dynamics component, and we added the human behavior into this. So first, from UF, I'm going to talk about how exactly we incorporated the signal and trajectory optimization into this framework. So for this, we picked up an optimization system that we are familiar with because we developed it here at UF. So this is basically the signal on the trajectory optimization framework. So there is a link to the published work if you are interested. So essentially, we developed this to be implemented in the field We have actually done some field testing with this framework as well. The summary of this framework is basically there is the sensor fusion system that takes in all the information of vehicle arrival through different sensors. Once we have the vehicle arrival information, we have something called as an intersection control algorithm that will do the optimization and produce optimal signal plans as well as optimal trajectories. So the optimal signal plan will be implemented at the signal controller, and the optimal trajectories are the trajectory recommendations are sent to the CAVs. So as you can see, if we were to implement this in a simulation framework instead of the signal controller, we would be sending this to the signal controller within the VSIM simulation framework. And the optimal trajectories have to be implemented in VSIM using the external driver module because of the reasons that I mentioned before. So how would we go about, implementing that? So this is how the modified or the updated simulation framework looks like. So we still do use the COM interface to get all the traffic information and the vehicle arrival information every time step into our optimization module. There are two types of optimizations that are happening. One is the signal optimization and the other is the trajectory optimization. So the signal optimization is sent back into the COM interface and to be implemented using VSIM's signal controllers. And then for the trajectory optimization, we write it onto a text file that gets picked up by the external driver module. So what are some of the challenges? So to begin with, to make sure that this particular framework is working, we just used 100% CAVs to test as a proof of concept. We use the same four-legged intersection that we used in the previous project. Instead, and we, to keep it simple, we just used a two-phase signal plan, and then we try to compare the performance in terms of delay with VSIM's signal plan versus an optimized signal plan. This is what we had with the 100% CAV. So we had 6 different scenarios with increasing demand levels. First 3 are evenly split 50-50. And next 3 are 70-30 with 800, 1600, and 2400 vehicles per hour as the vehicle network demand. So in terms of simulation result, for every single scenario, we had an improvement in delay. So delay reduced in each of the scenarios with at least 30% improvements. And then we saw more improvement when the demand was evenly split over a 70-30 split. So we said, and some of the problems we encountered are like the simulations runs very slowly, sometimes at or even slower than real time. And then, the reason is the way in which we send the information of the vehicle accelerations from the optimization module to VSIM is through writing on a text file. So that was the bottleneck that we found. So the next step was to now implement different combinations of CAVs, CVs, and conventional vehicles. So what are the challenges that we would face? So there are a couple of challenges. One was that with Rio, because it was using an assumed car following model for the leader vehicle, I believe it was a Gibbs car following model, it had like a certainty of where the leader vehicle is going to be. Whereas in this framework, as long as it's a conventional vehicle, the vehicle type is defined as a conventional vehicle, VSIM controls that, and there's no such certainty. And the second thing is within the optimization module, when the vehicle gets closer to the stop line, so the optimization and the iterations stop and the recommended trajectories get locked in. This works very well as long as the vehicle is a CAV and it will implement the recommended trajectory exactly as it was prescribed. But it doesn't happen so with conventional vehicles that are controlled by VSIM. So the solutions were to keep re-estimating the departure times for those vehicles, and then adjusting the network state, and also not locking for the conventional vehicles, not locking them with certain trajectory, no matter how close they were to the stop line. Of course, this meant more calculations and further slowing of the simulation speed. So to test this out, we came up with 11 different vehicle mixes with different percentage of CAVs, connected vehicles, and conventional vehicles. So 11 vehicle mixes and 4 demand levels with from 400 to 1600 vehicles per hour, and then 2 demand mixes, one even mix of 50-50, and then one at 70-30. So this resulted in 88 different combinations, and each combination we ran it for 5 times for multiple runs. And I have some results to show here. Due to lack of time, I'll be only showing like one set of results, but I will highlight different findings from particular set of results. So one thing that you notice on this table gives the delay difference between a VISIM operated signal control versus RIO, or the signal optimization software operated signal control. When you consider the average improvements across all the scenarios, all the 88 combinations that I mentioned, they're all positive. That's good news. There might be a negative in a few scenarios that is reflected in the minimum improvements that you can see on the left side on the first column. So some of that is because what happens is, some conventional vehicles, when they get stuck in a simulation, let's say VISIM has the 60-second rule where by default those vehicles disappear, whereas in the optimization it doesn't. So there's a discrepancy that is happening, which is causing some bottlenecks and delay times not improving. So what we did was we reran some of those scenarios with different random seeds, so that the vehicles that are stuck, which are not removed artificially like VISIM does, those are not counted. In general, what you can see is, all the scenarios that are at the top of your table, they're all like CAV heavy scenarios. So the CAV heavy scenarios have better performance compared to other scenarios in general. Some of the other findings that we found when we tried to redo this table with certain type of demands or certain type of vehicle mixes, what we saw was, in general, like we saw with CAV only case, the signal optimization software works better when demands are evenly split. And also, like we saw with higher percentage of CAVs, RIO performing better across all demand levels, irrespective of the demand, with higher percentage of CAVs. Whereas when the conventional vehicles are higher, the performance is only good at lower demand levels. So a mix of higher percentage of conventional vehicles and also higher demand levels is not a good recipe to get good improvements with at least the signal optimization that we used. So the conclusions from UF's work is, the initial implementation of the signal optimization module is working with the modified or the updated framework is working. And we were able to successfully run with different types of or combinations of vehicle types. The way in which we ran this whole system is very modular. So if someone wants to use their own signal optimization algorithm, they can use our existing with our modified framework, and then they can plug in their own signal optimization framework. We did observe slower and slower simulation speeds as the scenarios get more complex. The main reason being our accelerations are being written onto a text file that has to be read by the external driver module. So we did try to investigate whether we can do it in better ways. Due to constraints of time, we couldn't explore it further, and Georgia Tech helped us as well. We tried to see if we can use other functionalities that VISIM allows, to see if we can use those functionalities to transfer this information about the vehicle accelerations from the optimization module to the EDM in a better way. Some more work can be done on this area, so that the computation is not a problem. And finally, we only considered vehicle demand, and in the next iteration of this framework, we can include pedestrian demand as well. With that, I'm already a minute over my time, so I will hand it over to Dr. Sharif Gavish from Tennessee Tech to talk about incorporation of vehicle dynamics to the framework.
So hello, everyone. Thank you, Prudi, for this quick intro. And this part of the project, actually, I'm going to discuss the incorporation of advanced vehicle dynamics modeling for connected and autonomous vehicles with the microsimulation environment. This part, as Prudvi mentioned, was conducted by Tennessee Tech University under the supervision of Dr. Arman and Dr. Shireen. This task mainly actually focuses on enhancing the microsimulation performance by accounting for the vehicle dynamics, which will provide more accurate individual vehicle performance that can be incorporated with the microsimulation environment. Actually, several parameters have been accounted for in this simulation modeling, included driver characteristics, the vehicle body for different cars and trucks, as well as the power terrain, operational environment, as well as the operational modes. The vehicle dynamic model will provide distributions actually, or like it will provide at the end, the distributions and the performance distributions and curves for maximum acceleration, maximum deceleration, safe distance gap, as well as minimum safe time gaps that could be used within the microsimulation environment of this. The main, or like to this end, ransom or rank sim, which is the vehicle dynamic simulation tool was used actually to model and simulate the vehicle dynamics of 10 different passenger vehicles, as well as 4 different trucks. It accounted for, as I said, different operational modes, several driver characteristics. The vehicle power terrains used in this simulation or within this simulation tool were derived from this provided website, which is automobile.catalog. And the vehicle dynamics have been tested using the US 06 supplemental federal test procedures for passenger cars, as well as the cycle D for trucks, which are these 2 common or like well-known models for the performance for passenger cars as well as trucks. This table over here, it shows actually the different driver behavior utilized within this simulation or like the vehicle simulation environment as well. The simulated vehicles are presented here. These are like the different 10 vehicles as well as the 4 trucks, in which the parameters used for the simulation were the width, height, weight, the wheel radius, drag coefficients, initial and maximum engine speed, as well as the provided list down here. So all of these were actually simulated within the rank sim simulation, vehicle simulation, the dynamic environment. And the obtained actual, or like these different curves obtained from the previous mentioned website were factored in to effectively simulate these different vehicles or like the 10 vehicles as well as the 4 trucks. For sure, validation and calibration for the developed vehicle dynamic simulation were conducted, in which the truck sim and car sim were used to validate the performance of the simulated vehicles using the acceleration distance, in which like replication, we made sure that the values were replicated from the different truck sim and car sim modules, in which several assumptions were utilized as provided here in this list, in which we tested them also in different grades within the roadway profile as well. These are like some general conclusions and results obtained from the conducted vehicle simulation models, in which like it was found that the maximum acceleration is sensitive to the vehicle model and vehicle classification. Also, the vehicle model, vehicle classification and speed would affect the maximum deceleration, and the minimum safe gap distance is sensitive to the driving mode, different driving modes. And this table down here provide like the different ranges that were obtained actually for the different parameter, investigated 4 parameters: the maximum acceleration, deceleration, safe distance gap, and safe time gap, for the different parameters like the different truck types, car types, different tested speeds, as well as the driver characteristics and the different operational modes. So this like would conclude generally the different distributions and the ranges that can be utilized within the microsimulation of VISM and can be inputted to these microsimulation environments in order to simulate the different vehicles, accounting for the vehicle dynamics. So by this would conclude this vehicle dynamics part, and I would hand it again to Prudvi.
Thank you so much, Sheriff. So those were the first 2 changes that we did to the framework. So the first is the signal and trajectory optimization, and then the vehicle dynamics. The third one was to model human-driven vehicle behavior in presence of CAVs. So for that, we have our Drs. Michael Hunter and Anshuman Guane from Georgia Tech. Dr. Hunter.
All right. Thank you. So yeah, so next we're going to talk a little bit about considering the human-driven vehicle side of the AV equation. And the folks working on this project is myself, and Dr. Gwynn is also on the call, and James Abay who was the student working on it, has graduated. So he's successfully off doing some great things in industry right now. So just sort of a very quick background, and I'm not going to get into all the different pieces of the literature, but what you'll see is when you look at a lot of the AV modeling out there today, that the two most common customizations tend to be that, the AVs are assumed to be very cooperative, and they tend to have a conservative behavior, but also that the human-driven vehicles are usually assumed to be very cooperative, or that they'll treat a AV as if it's another human-driven vehicle. And that may not be true. I think there's some inclinations out in the literature. We can look at maybe the way folks have been treating some of the mobility service vehicles, some of the test beds that have been going on with AVs. There's a potential here that there's going to be some aggressive behavior towards AVs, and that a driver in one vehicle may treat a car that's being driven by a person differently than it would treat another car that's being controlled through an autonomous vehicle. So we want to sort of try to explore some of that. This builds off of some initial efforts we had done using Sumo, where we were looking at an off-ramp in that case, and just trying to see what would happen if I had these aggressive vehicles in the fleet. And in that case, and in the VisSim version as well, I'll talk about here in a second, we really break it up to three different vehicle types. One is the autonomous vehicle, which is assumed to be a cooperative, and then a human-driven vehicle, which is also generally assumed to be cooperative, and then an aggressive human-driven vehicle. So we break the human vehicles into two categories. One, more of a cooperative, that's the general assumption of most of the research today, and the other is a more aggressive. And in our version of aggressive, we're doing two things. One, we have them target the AVs. So the aggressive human vehicle, when it's trying to merge, it will go as far down the main line as it can, and to essentially cut off an AV and get its maximum advantage. And then the other aggressive part is when it cuts off, it will use very, very small gaps. And actually in the VisSim version, which we'll talk about, it will use basically no gap. It'll just force its way right in front of an AV and force that AV to hard brake if it needs to. So that's what we're really trying to look at, that impact. When we did this for the Sumo off-ramp version, we were able to show that we could do it. I'm just going to kind of basically what you really take from this is this idea that this is a time-space diagram trajectory, that the aggressive vehicle gains quite a bit of advantage, right? It's able to pass a lot of vehicles that are essentially exiting nicely on the off-ramp, move way out right to the tip of the gore and get itself off. Overall, on the off-ramp, when you look at averages, things don't seem to change all that much, but what really changes is who's receiving the benefit and who not. So travel time switches become very bimodal, with the aggressive vehicles picking up, right, really reducing their travel times, and the penalty being paid by the AVs and the just the regular human-driven vehicles, because they're caught in that same traffic stream. So if they're caught behind if they're caught behind an AV that is being cut off, well, they're going to pay the same penalty. So we decided to flip this around and look at, okay, so what would happen, maybe some capacity impacts, looking at an on-ramp situation. So now we're going to have an on-ramp, and we're going to look at sort of a worst case. We're really trying to kind of break out the parameters and kind of understand what the variables are. So we look at a single lane main line and also a single lane ramp. And then we're going to have the ramp essentially merge in. We are going to do two sets of experiments here. The first experiment assumes that there's no meter on the ramp. The second experiment, we're going to put a meter present to essentially sort of see if we can mitigate some of the effects we saw early on. And the experiments are going to be very directed at capacity. So we're putting way more demand on this thing, the demand coming from both the ramp and on the main line, than we can know it handles, because what we want to see is how much traffic can you push through the ramp junction. To do this, as I mentioned, again, now we're in the VisSim world now, so we're on the platform that we've been talking about. We have an algorithm to make this work. We've got our AVs, HDVs, and AHDVs. And AVs and HDVs are generally similar in terms of how we're modeling them. They're cooperative. AHDVs, right? We're not using any cooperative behavior in VisSim, and we're targeting. So essentially what's going to happen here is an AHDV will seek to maximize its advantage, get as far down the ramp as it can, and then cut off an AV. This takes, as Prithvi already mentioned, there's a few components here that we have to work with. We're doing the component object model, the external driver model, which with proof sheet mentioned. You got to use the COM, because it's basically capable of looking at all the attributes. You can get vehicle speed, lane position, type, essentially the objects of the model of your VisSim simulation, your component object model. Although it does have limitations, it can read most objects, but it cannot write to most objects. And the limitations are greater when you're in runtime. For instance, we can't force a merge, say right now, change lanes. To do that, you have to use your external driver model, which, as you've seen, the external driver model is very much about having, this is what people typically, if you want to do your own custom car following model, you would use an external driver model. We've also added in a user-defined attribute. The user-defined attribute is kind of a newer VisSim feature that allows you to create your own attribute, which we do, and we use it as a flag. So we use COM to do all the targeting. Once the targeting is all set, and it's time to merge, then we change that user-defined attribute that will turn the flag, and then the EVM say, oh, my turn, and the EVM will force the merge. The thing behind all this that is somewhat important is that you can't do this by just changing the vehicle parameters. I know, for instance, that VisSim has an AV. That only works if you're living within the basic underlying car following model and you want to just calibrate it. Here, we're really trying to change the behavior. We're saying we want to target. You do that, you start getting into all these things. So like we said, there's two basic scenarios. In one scenario, all the ramp vehicles are human-driven cooperative. In the other scenario, they're all aggressive, not very cooperative. And what you're going to see when you get into that is that you have aggressive vehicles, and when there's no AVs, the main line will keep running just fine. It's this yellow line is the total vehicles are through the junction. But once I even have just 2% AVs, just a few AVs, what will happen is this gray line here is the ramp. And the ramp basically takes over. Instead of the main line getting much traffic through, the ramp basically gets all its traffic through because I have these aggressive AVs, aggressive human-driven vehicles, and they're cutting off the AVs. And even if there's only a couple percent, they essentially just toward these giant platoons of aggressive vehicles, and the same AV might be cut off by 100 aggressive vehicles just going in, going in, going in. Now we know we've kind of built this to be sort of a worst case, but it's this idea that you kind of get stuck, that AV basically kind of gets stuck, and they just keep getting cut off. And if I move this traffic where it's not aggressive vehicles in the ramp, basically as we're modeling in most of the work today, then you'll see that doesn't happen, and that there's more of a balance down here, and that the main line still keeps its traffic moving, and the ramp is putting some on as well, but there's more of a balance. But if people get aggressive, so here's sort of another way to look at this, solid is aggressive, the dotted is not aggressive. The aggressive does increase overall junction capacity. So that's what this is, your overall junction capacity, which kind of makes sense because the aggressive are basically creating some much smaller gaps. So you're going to get a little more traffic in. But what you're going to see is solid line aggressive, dotted line not aggressive. On the main line, that even a very low percentage, that main line is going to get pushed way down, and the ramp is going to push a lot more. So this is the ramp traffic. I go from no AVs, I don't get much ramp traffic on, to just 2%. I get a ton more traffic on from the ramp, but I've essentially shut down the main line, which is this solid line, that the main line is not able to process more traffic. But if I look at the ramp, again, I can push ramp vehicles through when they're not aggressive. I'll actually get quite a few fewer vehicles on the ramp. So same deal, you're going to see this endless trade-off. Part of that, like I mentioned, is we also counted like how many vehicles would cut in front of a single AV. So when there's only 2% AVs out there, if cars are aggressive, you get a lot of cars just trying to cut in front of it, where when they're not, you're going to start to see some balance. And that's going to balance out too as you get more and more AVs, because there's essentially more and more targets to choose from. So what we did do then in the end was we added a ramp meter just to see, and I'm going to very quickly do that. You'll see when you put the ramp meter in, the total ramp junctions be same. Actually, the ramp meter buys you a little bit, but the big difference is, so this is the aggressive vehicles on the ramp, where before, without the ramp meter, they just took over and they shut down the main line. Now what happens is you're limiting the number of vehicles that can get on that ramp. So you're going to limit the number of vehicles that are able to cut off the AVs, and you can control that. And so now the main line, this is going to flip it. The main line actually will keep moving. So, and you can now reduce. So where we had a no ramp meter, your main line getting shut down, with the ramp meter, you can now sort of start to control those trade-offs and help the capacity as well. We'll skip that. I know we're running a little long, so I'm not going to get too much into this. You really got to do this stuff with EVM and COM. So we actually have created some documents. For instance, we have a nice document that we're just wrapping up right now on how you would actually do something like this in EVM. It's a little tutorial. So if you want to do this kind of stuff, It's very helpful that first time you do it, it's very painful. So this sort of walks you through your initial application. Like I said, the biggest hang up in all this is you got to have somebody who knows C++, and they're becoming fewer and far between. We're not going to dig too much into that at the moment. So what kind of walks away from this is it is really important that we start doing some of this kind of thing, because if we have aggressive drivers taking advantage of AVs, that the aggressive driving really does have a potential to significantly impact both capacity and travel times that we're not capturing if we don't reflect the potential of those kind of drivers. And the impacts are not experienced equally, right? So some vehicle types are really going to suffer where others don't. So you might look at average and say, oh, well, it's not that different. It might be significantly different to depending on where somebody is in their experience. AVs may be essentially getting shut down on the road because they're being bullied, because they're being targeted. So future impact we need to consider this, and we need to start realizing that we might have to start putting out some mitigations like ramp meters and some other things, simply to help control that, to act as gates to avoid that. And also when you're doing some of this modeling outside the box, like the platform we've been talking about, you're not going to be able to get away with just changing parameters in your Wiedemann models. You're going to have to look at how I handle SECOM, look at how I handle CEDM. Like, so we also use the UDA, which was kind of a creative way to sort of pass between the two of them.
This part of the task, this is task 6, Auburn and Tennessee Tech has been working on task to develop a CAV education material for transportation engineering course, mainly for the civil engineering student. This is what I'm going to present. The results from here is we conducted a national survey, try to identify the critical CAV topic for civil engineering curriculum. Those are the 7 least transportation engineering course offered by, I don't know, many universities, but this is what we offered here at Auburn. Introduction to transportation engineering, transportation planning, modeling, highway design, transportation safety system, and traffic engineering, traffic simulation, and ITS. So through this class, we like to add some lecture about CAV to each of these class. So that is the purpose. So this material can be used by other professors at other universities, so you don't have to spend similar amount of time by each faculty to develop similar material. So this is a survey we conduct for the national survey. We did the online national survey among transportation educator and also practitioners. We received 48 response. That's a result from representative from 33 states, include some faculty already integrated CAV in their class teaching, and also some practitioner already taught some the workshop on the CAV. So actually we put these two group of response, give them a little bit higher weight when we rank the topic. So this is a survey results. First, we identify a list of the potential topic put in the survey. Those potential topic is based on a literature review. This compiled based on previous CAV study or some existing CAV course already offered by different university and workshops. So the survey was designed for actually 3 groups. So if they are, we say, well, the answer is transportation engineer educator already incorporate the CAV into their course. They will be in a group of 1. So they will answer the question designed for them will be slightly different than other group. So we received 20 responses from this group. And the second group are the transportation engineer educator who have not yet included any CAV material in their course. I don't know what happened in your university, but at Auburn here, we have not included any CAV topic in those transportation engineering course. So we got 16 response for the group 2, and the group 3 we received 12 response for the practitioner. Some CDLT and some consulting firm they already conduct some workshop related to CAV. So So we ask them to rank the topic. For example, this is example ranking CAV topic for the course name. For example, Introduction to Transportation Engineering course. What kind of the topic you think about CAV we should cover in this kind of intro class? So this is an example question. What are the CAV level automation, CAV control concept, registration, overview, CAV pilot deployment, and that's each group. You see, each group they give a ranking for them, and we give a weight for each group. Then we got the weighted average, and based on weighted average, we can rank the topic for the class 1, 2, 3. For example, for the course this intro class, we select top 3 ranking the topic to include in the in that class. So eventually we based on the survey results, we identify those topics for each of these class. For the Auburn University team, we developed the material for first 4 class. Tennessee Tech developed for the traffic engineering, traffic simulation, and ITS course. So those are the topics for each different class. The format for eventually for the course material has been developed for each transportation engineering course. We include the material for 1 lecture is about 60 to 70 minutes class, around 35, 40 the PowerPoint slides. Each slide's content, you have student notes, you have instructor notes, and all the reference. So, and also we developed a class assignment example question. And those class, I believe after this project finish, we can upload the course material to an online link website, and you can, anybody want to use that can download to customize for your teaching purpose. So that's my presentation. I'm going to turn over to Dr. Sharif from University from Tennessee Tech to share his part of 3 course material he developed.
Again, as Dr. Hugo said, this was like collaboration between the 2 universities, and my part actually in developing the connected autonomous vehicle educational materials was mainly focusing on developing course materials for these 3 courses: traffic engineering analysis, as well as ITS and traffic simulation. As Dr. Hugo mentioned, again, in this task, several transportation engineering educational materials accounting for the effect of connected and autonomous vehicle technologies on different transportation fields were developed. And the focus, again, was to develop and provide the appropriate knowledge for engineering students about connected and autonomous vehicles and their influence on the different transportation fields. Actually, as he also mentioned, this would help in supporting the CAV testing and deployment, enhance the update current transportation engineering curricula, keep pace with the evolving automotive technologies, and provide the knowledge for engineering students. And the main deliverables, as usual, it's going to be like course notes, handouts, assignments, project courses, and so on. The main sources and references used in this effort actually were extracted from the Federal Highway Administration publications, the Society of Automotive Engineers publications, as well as reference manuals as the Highway Capacity Manual, Manual of Uniform Traffic Control Devices, as well as published research manuscripts. First, for the traffic engineering analysis, several aspects have been covered for this specific course, including the CAV impact on infrastructure, traffic flow, and vulnerable road users. The course also presents what are the different limitations associated with the CAV deployment and testing, as well as what are the current practices for CAV technologies, and what are the current regulations and recommendations and specifications out there in manuals or result of several task force committees as well. For the, again, for the traffic engineering analysis course, for the infrastructure, marking signs and signals were investigated. The effect of CAV on these different traffic control devices were highlighted. in which the CAF technologies were investigated or provide information how they can visualize the surrounding environment to operate safely and efficiently. What are the different challenges with the CAF technologies? For example, the low sun or glare, or maybe maintenance or non-uniformity of the different marking signs provided across the US. What about how they are going to perform in adverse weather conditions? Several challenges like these were highlighted, as well as different recommendations provided, for example, from the National Committee on Traffic Control Devices, in which they have this specific task force to investigate what kind of limiting or what kind of enhancement that needs to be provided for the current traffic control devices. Moving to the traffic flow, what is the effect of connected and autonomous vehicles on calculating the capacity of our roadways, on how to calculate the level of service, and so on. The latest highway capacity manual actually highlights specific sections within the whole manual actually on how to account for the presence of connected and autonomous vehicles, having these new tables for the adjustment factors of the CAFs. And finally, within this course, I discussed